Hello, this is Yukio Nagasaki from University of Tsukuba, Japan. What I'd like to talk about today is a poly-DOPA-based nanoparticle for Parkinson disease treatment with less dyskinesia. So let me tell you outline of this work. We designed amphiphilic block copolymer consisting of L-DOPA like this, which spontaneously form the polymer micelle with a 20 to 50 nanometer. We administer this and then accumulate in liver, hydrolyzed by enzyme and supply gradually in bloodstream to obtain sustained drug level, which improve therapeutic effect and decrease dyskinesia. Let me show you in detail. L-DOPA for Parkinson disease. The L-DOPA low molecular weight compound, water soluble and possess charge. When we administer this compound, due to the low molecular weight, problem is rapid metabolism, rapid excretion and diffusion to whole body. So we need to frequently administer, which decreases therapeutic effect and also gradually increase side effect. We hopefully keep the drug concentration for a long time. Otherwise, we cannot avoid, side effects like dyskinesia. As you know, drug delivery system, which means, encapsulation of drugs physically into nano carrier. But this is mainly focusing on cancer therapy because, nanoparticle tends to accumulate in tumor. However, recent studies show, the accumulation efficiency is only for few percent. Another problem is drug leaking from the nanocarrier, which means, after accumulation of nanoparticle in tumor site, but the nanoparticle itself might be empty. So this is due to the drug delivery system. So what we have focused on is a self-assembled drug. What does this mean? The creation of pharmacological function that occur only self-assembly, reduction of side effect unavoidable with low molecular weight alone, cheap and safe material design technology. Let me show you one example. We have so far focusing on antioxidant. When we administer antioxidant, which spread to entire body. So what is problem is, this antioxidant prevent very important electron transport chain in mitochondria of a healthy cell. So important loss must not be suppressed. So this causes severe dysfunction. What is important, overproduced loss must be selectively scavenged. Otherwise, we cannot use antioxidant. So due to the limit time, I cannot explain in detail, but we designed self-assembled antioxidant which prevent the adverse effect, dysfunction of mitochondria, electron transport chain, and only show, the antioxidant effect. So we applied this for Alzheimer disease because, Alzheimer generate reactive oxygen species by inflammation of amyloid fibrosis in brain. So this is some P8 mice and the normal mouse. So we monitored, time to find, the table and to rest. Morris water maze test. So you can see the normal mice takes 25 seconds, but the some P8 which generate amyloid beta in brain took around 60 seconds. we administer our self-assembled antioxidant to these mice and causes increase the cognition level like this. By avoiding the adverse effect of antioxidant, we can apply them for Alzheimer's disease. Today, let me show you, we have focusing on Parkinson disease using L-DOPA-based material. As I told you, we synthesize this polymer, polyethylene glycol and polydopa. As you know, polydopa is also hydrophilic, but we use protective acetyl group here and becomes hydrophobic segment. So this is amphiphilic block copolymer spontaneously form self-assembled structure, the size of which was around 20 to 50 nanometer. We administer this to animal by IP injection, and then the nanoparticle tend to accumulate in liver, and the enzyme in liver hydrolyze them and supply gradually L-DOPA in bloodstream. Let me show you pharmacokinetics. Using a mouse, we administer our self-assembled nanoparticle via IP injection, and then you can see low molecular weight L-DOPA increased concentration, blood level rapidly and decrease like this due to the excretion, metabolism, and spread to whole body. But in case of nanodopa, you can see the level of L-DOPA is extended for several hours to half day and did not increase too much due to the self-assembled structure like this. So AUC of L-DOPA, nanodopa, is 1 order of magnitude higher. So we confirm the therapeutic effect of our self-assembled L-DOPA by a Parkinson model mouse. We use grid walk test, resting tremor score, narrow beam walk test, and drug test. After administration of our self-assembled L-DOPA by IP injection, you can see here the therapeutic effect was observed like this. In case of resting tremor score, also show the effect of our nanodopa. So this is narrow beam walk test. Unfortunately, drug test did not cause any effect, but therapeutic tendency increased like this. So the final experiment is adverse effect, the dyskinesia using a large excess amount of L-DOPA. As compared to healthy and Parkinson model, we observed the higher Ames score by injection of a large amount of L-DOPA. However, in case of nanodopa, we use the same amount of nanodopa, L-DOPA concentration, but we could not observe any Ames score increment like this. Slide test also shows in case of L-DOPA decreases the latency time. On the contrary, the same amount of nanodopa did not decrease the latency time like this. So in conclusion, polyethylene glycol diacetyl L-DOPA block copolymer self-assembling drug was designed. Nanodopa improved therapeutic efficacy and suppressed undesired adverse effect, dyskinesia, by controlled supply of L-DOPA for an extended period. Thank you very much for your kind attention.